This is Unit 2F, Part 2. We've been looking at applications of the derivative, interpreting it as the slope of the tangent line. But another interpretation of the derivative is as the velocity given a position function. So if we've got some function like this one, s of t, that tells us the location of an object. In this case, our object is thrown upward from a particular height and allowed to fall to the ground. The height, which is the position, where it's located, is given by this equation. The velocity will always be the derivative of the position equation. So, in Part A, when I wanted height and instantaneous velocity at time 4 seconds, I'm going to start by saying the height is just s of 4. We just plug 4 into our s equation. And it looks like our height is 31.4 meters, right? At time 4 seconds. We can also calculate the velocity. Again, the velocity will always be the derivative of that position, so s prime of t. Plugging that in, or not plugging in yet, but taking the derivative, 2 times negative 0.8 would give me negative 1.6 t plus 4.8, and then just plus 0 for the constant term. And since I want to know the velocity specifically at the exact moment of time 4 seconds, we'll plug 4 into this instantaneous velocity equation. And we get negative 1.6. And that's a velocity, so it's moving at that many meters per second. The negative indicates that it's falling down. All right, Part B, we're asked for the impact velocity of the object. So how fast is it going instantaneously at the moment it strikes the ground? In order to figure this out, the first thing I need to know is when does it hit the ground, so that I have a time to plug into my velocity equation. Right now I don't have a time to plug in. So, first of all, I'm going to find the impact time. This is sometimes called the time of flight. How long is the object in the air? Well, at the moment of impact, the height is now 0. It's fallen back to the ground. So I'm going to set my s equation, my height equation, equal to 0. So 0 is equal to negative 0.8 t squared plus 4.8 t plus 25. That does not look like one that would be a lot of fun to actually try to factor. So I think I'm going to suggest here that you use your favorite quadratic equation solving method. You can do a quadratic formula. You can solve using an app on your calculator. You can solve graphically, just so we can all see. Why don't I do it graphically? I'm just going to graph that quadratic on Desmos and look at where it's equal to 0. Oops. So let's see, it was negative 0.8 t squared plus 4.8 t plus 25. And, oh, I need to put a y equals in here so it knows what it's doing. It's kind of cut off at the top, but I don't really care right now because what I wanted to know is when is this equal to 0. So it looks like at about negative 3.34 and also at about 9.34. Of course, the negative time would be before this object was ever thrown. So the one I really care about is the positive 9.34. So I'm going to say, from the graph, the appropriate t-value would be 9.34 seconds. All right, I now want the velocity at that time when it strikes the ground. So I'm going to say, let's take s prime of 9.34. Again, velocity being the derivative. So I'm going to go back up here to my s prime equation and just plug in 9.34. And I'm getting about negative 10.14. And again, that would be in meters per second. All right, in example 2, we have a particle's path given by the wave, s of t equals sine t cosine t, and it asks us to find the velocity of the particle at times pi sixths and pi. It says assume distances are measured in centimeters and time in seconds. So let's go ahead and do the problem first, and then we can talk about graphically why the answers make sense. Again, this is the path, so this is the location or position. If I want the velocity, I'm going to need the derivative of that position function. And in this particular case, I see a product here. So in order to do the derivative, I will need to think product, f times g. F would be sine t, and g would be cosine t, meaning f prime is cosine t, and g prime is the opposite of sine t. This is a product, so I'm going with fg prime plus gf prime. So let's see, this will be a little longer. Maybe I'll bring it down here instead. Fg prime will be a negative sine squared t plus gf prime. Gf prime would be a cosine squared t. All right, so we've now got a velocity function, and we were asked specifically for the velocity at 2 different times. So at time t equals pi sixths, our velocity, or s prime, of pi sixths would be negative sine squared pi sixths plus cosine squared pi sixths. And by the way, on something like this, if you have to plug in multiple times, sometimes it's nice just to go ahead and put your function in once. I've got my derivative there, and then I can just go to the table. Oh, one more thing. Let's make sure I'm in radian mode. I am, so we're good. So if I go to my table and I plug in pi sixths, looks like I'm going to get 0.5. And this would be centimeters per second. And then we can also do our time of pi seconds. My velocity would be s prime at pi. That one's probably almost easy enough just to do in my head, but we can use the calculator as well. Sine of pi is 0 and cosine of pi is negative 1, right? So we should get 1. And there it is, at pi our velocity is 1. Let's take a quick look at the graph of this function and talk about, how these perhaps would make at least a little bit of sense based on those graphs. So I'm going to graph sine x, cosine x, or sine t, cosine t. And let's see, I don't really need such a large graph here. Let's just go ahead and on my settings, on the x-axis, I'm going to go from -2 pi to pi, or to 2 pi. And on the y values, I'll go from -2 to 2. On the x values, let's set a step size. Let's count by pi/6. Make it easy to figure out where I am. And there we go. So you can see that this object is moving in the positive direction. And my first pi/6 would be right here, right? Every tick mark down here is pi/6. Excuse me, I thought it was. No, it wouldn't be. Didn't I do that? Step size pi/6. All right, I thought it was going to give me mark things off in pi/6, but it didn't. Looks like it did pi/4, but that's all right. So pi/6 would be a little less than pi/4, so it would be over here somewhere. And at that point, if you look here, the tangent line would have a positive slope. The tangent line, slope of the tangent line, is also the velocity. They're both the derivative. So the fact that we got positive 0.5 seems reasonable there. Our other time was pi, which is right here. And again, right at this point, you can clearly see that the tangent line would have a positive slope. In fact, a slightly steeper positive slope than up here, where it was already a little bit less. So that velocity of 1 makes sense. This is kind of putting those two ideas together. The idea that the slope of the tangent line is the derivative, and the velocity is also the derivative. So you can estimate velocity off of a position graph by thinking about the slopes of the tangent lines. All right, that's the velocity example, so we will pause here and we'll finish up our last examples in the next video.